Okay, in the last lecture, we have seen how to find the analytic function when the real part u is given, or the imaginary part v is given, or the algebraic sum, that is u plus v or u minus v is given. Okay, now we have to move forward. We have to see some another concept or more concepts related to the analytic function. So let us see the harmonic function. So what is the harmonic function and how it is related to the analytic function? I hope you are able to see my screen.
Yes, sir.
So today we have to see the harmonic function, and we have to see how this harmonic function is related to the analytic function. Okay, so let phi equal to phi of xy be the function of x and y. The function phi is said to be harmonic function if it satisfies double square phi by double x square plus double square phi by double y square is equal to 0. That is, we can write this as del square phi is equal to 0, where del square is equal to double square by double x square plus double square by double y square. Okay. So actually, del in 3 dimension is I double is going to be I double by double x plus j double by double y plus k double by double z. So if I consider del square, then it will be del dot del, and so it is del square double square by double x square plus double square by double y square plus double square by double z square. This is the del operator in 3 dimension. So we are in complex number, so we are with only 2 dimension x and y, and that's why del square is written like this. Okay, so this is the general definition of del, and then you can extend this to as many directions. This I have written in 3 dimension, but you can extend this to n dimension. Okay, so here we have to consider this only. Okay, so we can say the equation del square phi is equal to 0 is called Laplace equation. This is called Laplace equation. Yes. So we can redefine this harmonic function as, yeah, the function phi of xy is said to be harmonic if it satisfies Laplace equation. So if this function satisfied Laplace equation, that is del square phi is equal to 0, then we say it is going to be the harmonic function. Or what easy way we can say, del square is what, double square by double x square plus double square by double y square. So if the sum of these two second order derivative is going to be 0, then we say this function is going to be a harmonic function. So if it is a harmonic function, how it is related to the analytic function? Because we are exploring about the more about the analytic function. So the question is how it is related to the analytic function, and hence we have, okay, so let f of z is equal to u plus ib be an analytic function, then u and v are harmonic functions. So that is what you can say is double square u by double x square plus double square u by double y square is equal to 0, and double square v by double x square plus double square v by double y square is equal to 0. Okay. So this u and v both satisfy the Laplace equation. Okay. What is the condition? The condition is that if this is the analytic function, then definitely these are the harmonic functions. Okay. So the question is, can we say vice versa? So if v and u are the harmonic function, then can f of z be the analytic function? Then answer is no. We can't guarantee. Though u and v are the harmonic functions, but we can't guarantee that f of z equal to u plus iv is an analytic function. So it is one way that if f of z is analytic, then u and v are harmonic. But either way, it is not true. Okay, and that's why we have to be careful. So if we know this is harmonic, then these are. If we know this is analytic, then these are harmonic. And moreover, we have to consider one more concept. Okay, so what we have here. So if f of z is equal to u plus iv is an analytic function, then u and v are called harmonic conjugates of each other. Okay, so that is u is harmonic conjugate of E, and E is harmonic conjugate of. Okay, so this is how this harmonic concept, harmonic function, is related to the analytic function. So if the f of z is analytic, then these are harmonic. And moreover, these u and v are called harmonic conjugates of each other. Okay, and if they are harmonic conjugate of each other, definitely we are able to find if we know one of them. Okay, so what is the path? So if I know u or v, then I am able to find out this f of z, and once I know f of z, I am able to find out its real and imaginary part. So that's how we are able to know if u is given, we can find v. If v is given, we are able to find u, as we are able to find the analytic function f of z. Okay. So now, so is this concept of harmonic function clear to you? So is there any doubt in this concept of harmonic functions?
So can you repeat?
Yarthi?
Sir, can you explain it again?
Okay, no problem. Yes. So uh, what we have, when we say a function is harmonic function, suppose we have a function phi of x and y. Okay, so this function of two variables x and y is said to be harmonic if we have double square phi by double x square plus double square phi by double y square is equal to 0. Okay, what this means? This means that we have to find the second order derivative of this phi, and after finding the second order derivative of this phi, if we get their sum to be 0, then we say this function phi is harmonic function. Okay, this equation particularly is called Laplace equation. Okay, so this equation particularly is called Laplace equation. Now, from where this del operator comes, or what is this del operator? So, del operator in general is written as I double by double x plus j double by double y plus k double by double z. This is in the three-dimensional I have written. You can go for n dimension also. Then I will take double square del square. So del square is what? Del dot del. So we know the vector product. Okay. So here we have del dot del. Now, if it is del dot L, then we know for vector dot product, we have the corresponding multiplication. So this multiplied by this will have the square of all. Now, complex plane is a two-dimensional. So that's why we consider only first two coordinates. Okay, so we consider x and y, and that's why this del square is as double square by double x square plus double square by double y square. Okay, and we call this equation as Laplace equation. So we can redefine this equation, this concept as if the function, okay, if the function phi satisfies Laplace equation, then it is harmonic function. Now the question is how this harmonic function is related to analytic function, because we are exploring analytic function. Now what we know is we know f of z is going to be analytic. So if f of z is equal to u plus iv is an analytic function, then we can guarantee that this real part and this imaginary part both are harmonic functions. Okay, and now these are harmonic functions. That means what? They will satisfy the Laplace equation. Okay. Moreover, so if f of z is an analytic function and u and v are harmonic functions, then we can say u and v are called harmonic conjugates of each other. So if we know that f of z is analytic function, then its real part and its imaginary part are the harmonic conjugates of each other. So we can say u is harmonic conjugate of v, and v is harmonic conjugate of u. Okay. So you got this concept now, or is there any doubt?
No, sir, I got it. Thank you.
Okay. Yeah, that's good. Okay. So now we'll try some problems based on this. Okay. So let's have the problems based on yeah. What is the harmonic conjugate? Okay. So as we have a pair here, f of z is analytic, and hence the imaginary part and real part of this function, analytic function, these are called the harmonic conjugate. This is the definition of harmonic conjugate. So we can have. Okay, so let's have the examples based on this concept. Okay, so go with the example, then it will be more clear to you. Okay, do that u is equal to bx square y minus y cube is harmonic function. Okay, this is going to be harmonic function. Okay, so with the solution, like always write the given thing. So u is equal to ex square y minus y cube be the function of x and y. Okay. Now see, we want to prove this function to be harmonic. So what I have to prove is I have to prove this equation, or I have to prove that the function u, given function u, satisfies Laplace equation. Okay. So to have the Laplace equation, we have to find the derivatives, precisely the second order derivative of this u and u with respect to x and y. Okay, so now let us find the derivative of this u with respect to x. So we'll be having here 6xy, and we'll have double square u by double x square. Again differentiate this with respect to x, so we get 6y. Okay, and now we differentiate this u with respect to y. So we have here 3x square minus 3y square. And we differentiate this again with respect to y. So we have here, this is minus 6y. That is equation 2. Okay, now you can see what we have to do is we have to find the sum of this two second order derivatives. Okay, so let us find the sum of these two second order derivatives. So adding equations 1 and 2, we get, so what will have, double square u by double x square plus double square u by double y square is equal to, we can have 6y minus 6y, and that's going to be 0. So you got here okay. So we have here, this is going to be 0. And hence, what you got here? We got double square u by double x square plus double square u by double y square is equal to 0. Okay. So we proved that the sum of the second order derivatives for this u is going to be 0. So we can say here that is Laplace equation is satisfied. Okay, and if Laplace equation is satisfied, then what you can say is, then we can say u is harmonic function. So here we proved that u is going to be harmonic. So what we did here, we just consider the function, then we calculated the second order derivative, and then we calculated what is the sum of these two second order derivative, and then it came to be 0. So we said that Laplace equation is satisfied. So as the Laplace equation is satisfied, we can conclude that the function is harmonic function. Okay, and hence we go with the another example. Okay, so let's have show that the function u is equal to half of log of x square plus y square is harmonic function. Okay, so that's what we got. Let's go with the solution. Okay, what we know, what we have to do is always write the given thing. So let u is equal to half of log of x square plus y square be the be the function of x and y. Okay, now consider w by x. So we have to find the derivative of this. This half remains as it is, 1 upon x square plus y square, and the derivative of this term, so it is going to be 2x. So what we got here, this 2 and this 2 will get cancelled, so we'll be having x upon x square plus y square. So we get w by x is equal to x upon x square plus y square. Now we have to find the derivative of this term with respect to x again. So we can have w square u by x square is equal to u upon v rule. So x square plus y square into 1 minus x into 2x upon we have x square plus y square bracket square. So here if we simplify, x square plus y square minus 2x square upon we have here x square plus y square bracket square. So we have here w square u by x square is equal to, we can write y square minus x square upon x square plus y square bracket square. Let this equation 1. And now we have to differentiate this with respect to y. So let us differentiate with respect to y. So we have w by y. So we can have half 1 upon x square plus y square and the derivative with respect to y. So this 2 will get cancelled. You will be having y upon x square plus y square. So we get here w by x is equal w by y is equal to y upon x square plus y square. And now we have to differentiate this with respect to y again. So w square u by y square is equal to, so we will be having x square plus y square into 1 minus y, and this is 2y. Okay. And now what we have here in the denominator, we have x square plus y square bracket square. Okay. So simplify this, we will be having x square plus y square minus 2y square upon x square plus y square bracket square. And Double square u by double y square we get as x square minus y square upon x square plus y square bracket square. That is equation. Okay. So see, we got the second order derivative with respect to x. We got the second order derivative with respect to y, and hence we can have the addition of these two. So let us see what happens to the addition. So what we can do is adding equations 1 and 2. We have, so what will be having double square u by double x square plus double square u by double y square is equal to. So first we have y square minus x square upon x square plus y square bracket square, then plus x square minus y square on x square plus y square bracket square. So this we can write as y square minus x square plus x square minus y square upon we have x square y square plus y square bracket square. Okay, so you can see that yeah, so this x square will get cancelled with this x square, this y square will get cancelled with this y square. So we can have 0. And as we have 0 in the numerator, so denominator doesn't matter. So what we get is double square u by double x square plus double square u by double y square is equal to 0. So what we have here, so that is Laplace equation is satisfied. Okay, so we can say Laplace equation is satisfied. And once we have the Laplace equation satisfied, so we can say the function is harmonic. So we can say the function u is harmonic function. Okay, so this is going to be the harmonic. So this way we are able to prove the function to be harmonic function. So do you have any doubt in these two examples? Uh, but where is V you have? We are just we are just checking for the harmonic function, whether it is harmonic or not. We are just checking for harmonic function. Okay. Yeah. No need to say sorry. It's okay. You can ask any query. That's okay. So, do you have any doubt in these examples? We'll solve one more example then. Okay. So let's have the another example. Okay, that's good. So we'll go another example. Show that the function is equal to e raised to x cos y plus sin y plus x square minus y square is harmonic. Okay, so we have to show that this function is going to be harmonic. Okay, so let's have the solution. So let t is equal to e raised to x cos y plus sin y plus x square minus y square being the function of x and y. Okay, so we have this the function of x and y, and now we have to find out the second order derivative. So what we can say is consider. Okay, so we have to find the derivative of this with respect to x. So dabba b by dabba x is equal to. So when we are finding the derivative with respect to x, this y terms will be constant. So the derivative of e raised to x is e raised to x, solving cos y plus sin y remains as it is. Now here plus the derivative of this term will be 2x, and the derivative of this term is 0. Now we have to find the second order derivative of this one. So dabba square v by dabba x square. Again, the derivative of e raised to x is e raised to x cos y plus sin y remains as it is, and plus the derivative is going to be this 2. So we have this is equation 1. Okay, and now we have to consider the derivative of b with respect to y. So the term of e raised to x remains as it is, and the derivative of this term. So the derivative of this cos is going to be minus sin y, and plus this is cos y, and the derivative of this term is going to be 0. So derivative here we have minus 2y. And now I can write this as dabba v by dabba y is equal to e raised to x cos y minus sin y minus 2y. And now we find the derivative of this first order derivative again. So we have dabba square v by dabba y square is equal to. So e raised to x remains as it is. The derivative of this is again minus sin y. This is minus cos y and minus 2. So this is going to be the equation 2. Now we got the second order derivative with respect to x. We got the second order derivative with respect to y. And so we are able to write the sum of these two. So what we can do is, we can say adding equations 1 and 2. So we have, what is the term we'll have here? See this. Okay, dabba square v by dabba x square plus dabba square v by dabba y square. So this term is e raised to x cos y plus sin y plus 2. This term is plus e raised to x minus sin y minus cos y and minus 2. So we can write this as e raised to x cos y plus sin y minus sin y minus cos y. And this plus 2 minus 2 will get 0. So this will also get 0. As sine term will get cancelled, cosine term will get cancelled. And so what we get here, we get dabba square v by dabba x square plus dabba square v by dabba y square is equal to. So what we got actually, so we can say that is Laplace equation is satisfied. Okay, so if the Laplace equation is satisfied, we can say the function E is harmonic function. Okay, so this function is going to be harmonic. Okay. Now, do you have any doubt in this example? Okay. Do you have any doubt? No doubt. Okay, that's good. So here we have shown that the function is harmonic. Okay, now the next is how to find harmonic conjugate. Okay, so that we have to see now. Now we have to find the harmonic conjugate. Okay, so once we can understand the given function is harmonic, so we are able to find the harmonic conjugate. Okay, now to find harmonic conjugate, we consider the following steps. Okay, so what are the steps we consider? So when we know the function is harmonic and we have to find out the harmonic conjugate, that means we must have an analytic function. So we consider f of z is equal to u plus iv p and analytic function. Okay, so with the real part u of xy and imaginary part v of xy. Okay, so either u will be given to you or v will be given to you. Then we know f of z is equal to u plus iv is an analytic function. Now, the second, use Milne-Thompson method to find analytic function f of z. And third step, put z is equal to xy in f of z and separate real and imaginary parts. Okay. So once you separate the real and imaginary part, so if u is given, then you will get v as a harmonic conjugate. If v is given, then you will get u as a harmonic conjugate. Okay. And these are the three steps we have to use to find the harmonic conjugate. But when we say these are the three steps, you know, in Milne-Thompson method, there are many steps. So we have to use those all steps here. Okay, and then we at finally we have to separate the real and imaginary part. And once you get your required, so you must able to recollect what is given, and if what is given is correctly recovered, then you can say the other remaining is the required one. Okay, so suppose u is given, then you are able to recover u properly in the final step, then you can say you got the correct v. If you are not able to get correct u, then you might have committed mistake in calculation. Okay, so let us try to have an example based on this answer. Okay, so we can think of example. Okay, show that u is equal to x cube minus b xy square plus 6xy is harmonic function, and hence find the corresponding analytic function f of z and its harmonic. Okay, so we have to find the corresponding analytic function and harmonic conjugate. So you can see what we have to do is we have given u, we have to find out f of z, and then we have to find out its harmonic conjugate. Okay, so exactly these are the three steps that we have to follow for this example. So let's have the solution. So what is the first step we have laid? F of z is equal to u plus iv p and analytic function with real part u is equal to x cube minus 3xy square plus 6xy. Okay. See, this is the real part given, so we have to use the Milne-Thompson method for the real part. So what is the second step? We have to show here also that this is a harmonic function. So consider phi1 of xy is equal to w by w(x). So we got here 3x square minus 3y square plus 6y. Let this equation 1. Now to show a harmonic function, find out the second order derivative. So w square u by w(x) square is equal to 6x, and the derivative of this term is going to be 0. So you can have this is going to be equation 2. Now we have to find out the derivative with respect to y. So now we have phi2 of xy w by wy. So the derivative of this with respect to y, we can have minus 6xy and plus 6x. So let this equation 3. Now again differentiate this with respect to y. So we can have w square u by wy square. So it's going to be minus 6. The derivative of this term is going to be 0. So we can have equation. So to show that this function is harmonic, we have to add 2 and 4. So we can have here adding equations 2 and 4. We have. So what we'll get is w square u by w(x) square plus w square u by wy square is equal to 6x minus 6x is going to be 0. Okay. And hence what we get here, we get w square u by w(x) square plus w square u by wy square is equal to 0. Okay. And hence what we can say is that is Laplace equation is satisfied. Okay. So Laplace equation is satisfied here, and hence what we can do is, so we can say that this function u is harmonic. So we can say the function u is harmonic. Yes. So the first part of this example we have proved that we wanted to show that this is going to be harmonic function, and we have shown it is harmonic function. Now we have to find the corresponding analytic function. So to find this corresponding analytic function, what we have to do is we have to use this equation 1 and 2. So the two steps of Milne-Thompson method already we have completed. Now we have to go to the third step, and hence we write put x is equal to z and y is equal to 0 in equations 1 and 3 we get. So what you are able to get is phi 1 of z0. Okay, see what is phi 1 of z0. So here this will be 3z square, this will be 0, this will be 0. Okay, this is the term you'll be having here. We get this is going to be 3z square, and we have phi 2 of z0. So what is phi 2 of z0 we have? Here y is 0, so this term will be 0. So we have here 6z. Okay. So we got here, this is going to be 6z. The third step is completed, and hence we'll have the fourth and the final step of Milne-Thompson method. So what we can say is by Milne-Thompson method, the analytic function f of z is given as. So what you can have is f of z is equal to. So here we have phi 1 of z0 dz minus I integral phi 2 of z0 dz plus c, where c is constant of integration. Okay. So that's what you'll be having. And hence write down what we have phi 1 and phi 2. So this is 3z square dz minus I. This is 6z dz plus c. So we got here, this is 3z cubed by 3 minus I. This is 6z square by 2 plus c. So you have z cube minus I. So you will be having here 3z square plus c. So we got here f of z is equal to z cube minus 3iz square plus c. Again, so this is what we got analytic function. So we can say is required is uh, required analytic. So we got the second part of the example completed here. Now we have to find a harmonic conjugate, and hence the third step. So what we can do is put z is equal to x plus iy in above equation. So we get. So here we have to put again back is z is equal to x plus iy bracket cube minus 3i x plus iy bracket square plus c. Okay. So we have to simplify this. What we know is a plus b bracket cube is equal to a cube plus 3a square b plus 3ab square plus b cube, and a plus b bracket square is equal to a square plus 2ab plus b square. Okay. So using this formula for the expansion, we are able to get x cube plus 3i x square y minus 3xy square minus I y cube. Here what we have, I square is equal to minus 1, I cube is equal to minus I, and then minus 3I. So we have x square plus 2I xy and minus y square plus c. Okay. So simplify this, we can have x cube plus 3I x square y minus 3xy square minus iy cube. We can have this as minus 3I x square minus y square, and you can have this plus 6xy plus c. Okay, this minus this minus will I square, you'll have minus, and minus minus will become plus. Now we have to separate the real and imaginary part. So we have, this is f of z, and hence f of z is equal to x cube minus 3 xy square plus 6xy plus I b x square y minus y cube minus you can have, this is 3x square plus 3y square plus 6. Okay. So now we have to verify whether our answer is correct or not. Okay. So what I said is, if you are able to recover the given part properly, then your answer is correct. So what is the given part? The given part is u. So it is x cube minus 3xy square plus 6xy. Okay. And you can see what we have obtained. Okay. So it is x cube minus 3xy square plus 6xy. So we have correctly obtained the real part, and that's why we can say this imaginary part is correct. So we write here, comparing real and imaginary parts. We have u is equal to x cube minus 3xy square plus 6xy, and b is equal to e x square y minus y cube minus 3x square plus 3. So what we know is, we know that b is the harmonic conjugate of u. Okay, so we can say the harmonic conjugate of u is, okay, so we can write b is equal to e x square y minus y cube minus 3x square y x square and plus 3 y square. So this is what having the harmonic. So see here, we followed exactly the same steps that I have given to you. Okay. So what we did is, our first step was to write this, then prove here that harmonic function, it is a harmonic function. Now we use Milne-Thompson method, and we calculated the real and imaginary part, and then we got the harmonic conjugate. Okay. So this is how we are able to get the harmonic conjugate. Okay. So do you have any doubt in this example? Do you have any doubt in this example? Okay. So that's good. We don't have any doubt.